Okay, so we talked about the energy that you get for magnetic states of nuclei with E of m sub I. This is the energy along the z direction, and that's going to be in the plane or in the direction of the magnetic field. And so if you have the magnetic field pointing up, B0, then there's going to be some spin quantum number I that's going to then be projected, and m sub I is then your projection of the angular momentum onto the z-axis. Cool, we're familiar with that language. Okay, here's the fun part about the resonance technique. So this is an energy state. So G. In an absorption technique, you've got an increase from this state to this state. I'm going to pause real quick. There we go. I just adjust the windows and the monitor, so now you can hopefully see the board better. If it's an absorption technique, you have some lower energy state, psi1, higher energy state, psi2, photon comes in, the electron doesn't jump up, it just goes from lower energy state to higher energy state. I liken this to me drinking my coffee, right? I'm not moving, I'm just going from low energy state, higher energy state, yay caffeine. Okay, that is not what's happening here. Resonance technique. In no magnetic field, so B equals 0, the energies of the spin states are all degenerate. Okay, they aren't, there isn't a difference between the energies associated with the spin states in the absence of a magnetic field. When you have a magnet, so when this is 0, these are, well, it's not 0 really. This only actually applies when you have what's called degeneracy lifting. When B doesn't equal 0, these energy states are going to split. Okay, and so you can think of this then as degeneracy lifting, also known as the Zeeman effect. I guess technically it's a Stark effect. Or Zeeman splitting. So in the presence of a magnetic field, these states split, and you're left with a certain number of spins in the alpha state and a certain number of spins in the beta state. So that's the notation that we're going to use. So this would be m sub I is equal to plus 1/2, and this is m sub I is equal to minus 1/2. I should say that this is specifically for nuclei with half integer spin. Okay, so this is for half spin. Slightly different than for integer spin, but the concept's the same, but the diagram would be slightly different. Okay, so this is the energy splitting that you have, and it's this energy difference, this delta E, that incident photons are then in resonance with. Okay, how do I mean that? I've got 4 spins in the alpha state and 3 spins in the beta state. It's not that alpha is the ground state and beta is the excited state. Doesn't work that way. You have essentially equal numbers of alpha and beta states occupied, but what happens is there's a very, very, very small percentage of nuclei that have spins in the alpha, slightly higher. So if this is like 50.002, and this is 49.9998 or something like that. So it's just a very subtle, slight increase, such that this one spin state can flip orientations with, so in one case it's with the magnetic field, or with the magnetic field, and the other case it's not with, it's anti-parallel to the magnetic field. And so this one would flip orientations, and that's where this idea of spin flipping comes. It's not that all of them exchange. It's not, it's just the 1 or 2 that are in the state that they can then jump up to this higher state, or not jump up to the higher state, flip their spins to be in the higher energy state. Okay, so the energy here, E, is going to be equal to minus gyromagnetic ratio, B0, H bar over 2, so that's multiplied by plus 1/2, and then E is going to equal minus gamma n, E0, H bar minus 1/2, Okay, so notice how this has a negative sign, this one has a positive sign. That's why I designated this one as positive, or this one as the m sub I is plus a half, because that's going to be the lower energy state because of that negative sign. Okay, but I care about delta E, which if I take this state minus this state, E of m sub I is equal to minus a half minus E m sub I equals to plus 1/2. I get gamma H bar E0. Prove that to yourself. Okay, so for what we call the resonance condition, I have an incident photon coming in, H nu, that's going to be equal to gamma H bar E0, such that if I then solve for what the frequency is going to be, I get gamma E0 H bar over H, which is nice because then my H's can cancel. Oops. H over 2 pi H. Okay, so this frequency here is the frequency of an incident photon that comes in that will then be in resonance with the split spin states and will cause this spin state to then change its orientation. Okay. This is a very specific type of frequency. It's tuned to certain nuclei in certain magnetic fields. But notice, this is proportional. Right? Again, the frequency is directly proportional to the magnetic field. So depending on the strength of the magnetic field, little magnetic field, little frequency, big magnetic field, big frequency. Okay, so this is not specific to nuclei, it's specific to nuclei in particular magnetic fields. Okay, and this is called the Larmor frequency. Give it nu sub L. Okay, kind of neat. It is in the radio, so this is radio spectroscopy really. So this will be in the radio frequency, and for typical NMRs, you're in about 500 megahertz frequency for a typical NMR. Ours is 400 megahertz, which is why ours is known as the Varian 400. Go team. Cool. That's all I want to say about that for now. Now I'm going to jump into, let's look at the population differences between alpha and beta.